So, okay, so looks like it's time. So let's get started. Go ahead whenever you're ready.
Sure, I'm ready. So I told you that we are going to go slow with the different versions of revenue equivalence principle. So let me tell you before moving on to the deviation from it by considering two important aspects. The first one is going to be risk aversion. The second one is going to be asymmetries. But before that, again, this is not on the slides. I'm going to write it here. Just follow me to get the first version of the revenue equivalence principle. So previously in the first class, we established that the revenue between first price and second price auction is the same, but this is not a coincidence. It will be actually the same revenue for all the auctions in which the allocation will be efficient. So we are going to have a definition of a standard auction. A standard auction would mean that an auction is standard when the highest bidder wins. Okay? And then with the monotonicity and symmetry assumption, this will result in the efficient allocation, which would mean the winner of the auction is going to be the bidder with the highest value. And all these auctions will result in the same figure. This is the revenue equivalence principle. So as I told you, an auction is standard. If the rule of the auction dictates the highest bidder is awarded the object. Now the proposition is we have private values with IID distribution, independent and identity distributed signals, and risk neutrality. Then any symmetric and increasing equilibrium of any standard auction I'm going to put a comma here such that expected payment of a bidder with value 0 is 0. So I'm here assuming that like the lowest of possible values is 0, but we don't have to assume that actually. We can also consider a case in which like the values are distributed between V lower bar and V upper bar, and that should also hold. All we have to do is to change this V 0 here to V lower bar. So among all those, like with this caveat, such that the expected payment of the bidder with the lowest value is 0, yields the same revenue, and this will have a simple proof. Okay, so we are going to just like consider an arbitrary standard auction. Let's consider the interim expected payment in this arbitrary standard auction to be MA of X. Okay. So this is the interim expected payment, and by definition, like here with the caveat here, right? We know that MA 0 is 0.
So what's the A?
And the A represents any auction. Any auction. Yeah. So now, similar to what we had done before, let's consider the utility of a bidder with value Z, but who bids as if his value is, I'm sorry, utility of a bidder with value X who bids as if her value is Z. You can write this one as G of Z times X minus MA of Z. Right? Because if I bid as if my value is Z, I only win when all the other bidders have values smaller than Z, because I'm considering a symmetric and increasing equilibrium. And then in that case, I am going to get X. X is my value. And then MAZ is my interim expected payment. Right?
So when you say standard auction, you mean the simultaneous with
yeah, so we are considering a symmetric, like basically, for some dynamic auctions, you can also consider simultaneous representations of it, yes, but this is a symmetrical. This is a simultaneous volume. This is a normal only. So everybody is basically announcing the like. I'm not yet using revelation principle yet, but yeah, think about this as a simultaneous auction.
But I guess you're excluding English auction.
Yeah, English auction. So English auction, I'm not really excluding in a sense that like you can kind of argue that with private values, it is equivalent to a second price auction, and second price auction is included. So, but no. So basically, when I say standard auction, I mean a simultaneous move game, not a dynamic game. All right, very good. So this is the interim expected payment when you behave as if your value is Z. Okay. So for this to be an equilibrium, this needs to maximize when Z is equal to X. So that means that at an interior solution, with the assumption of differentiability, the derivative of this with respect to Z evaluated at Z is equal to X has to be 0, right? So then you get G of Z times X minus MA prime of Z evaluated at Z is equal to X is equal to 0. So this means that just substitute is equal to X everywhere. So X GX minus M prime MA prime of X is equal to 0 for all X. Then now all we have to do is we just take the derivative, right? So that means that we're going to just erase it and write it here. So this is a very simple proof basically. So this says that then MA of X, interim expected payment in any standard auction, is 0 to X, Y, GY, DY plus MA of 0, which is the constant of integration, right? So when I take the integral of both parts, I also need to add constant of integration. But when X is equal to 0, this just becomes 0. And with the assumption that the lowest valued bidder will have a 0 expected payment, then this also becomes 0. So we just ignore this part. And then this shows that in all standard auctions, interim expected payment is this thing that we have seen for the first price and second price auctions. All right. So let's do a very simple exercise. So using
So here, well, let's assume the differentiability. So, I was about to ask you, so previously in the first price auction, you made a point that the only possible deviation you need to worry about is to pretend to be another type.
Yeah. Yeah.
And then I was about to ask you whether that's what the still the same here or not, but maybe is that we are not
So
we don't even need to think about it because it's just a necessary condition that the
this is we are just talking about a necessary condition. So assuming an equilibrium exists. So like there we are also showing that equilibrium is indeed an equilibrium by considering global deviations, right? Remember this picture proof. Here, let's say that there exists an equilibrium.
I see.
If that equilibrium exists, this has to be satisfied. Therefore, this has to be satisfied. So like essentially will be relevant. So for instance, like we will have two applications of quick applications. One of them is all-pay auction, and the other one is like third price auction, which is a theoretically interesting case to consider. But it will turn out that, for instance, we will get a result, but this result, the equilibrium that we identify using this revenue equivalence theorem, may not be, for instance, monotone for some value distributions. So that would necessarily mean that for those value distributions, what you calculated is not an equilibrium. Because this is like, assume an equilibrium exists of this kind and then show that this has to be satisfied. And actually in many auction theory papers, like this is called a first order approach. So except for exceptions, in many auction theory papers, you do not have like kind of like existence proof in the appendix. In some you do, but in some you don't. So you just say that you just like say that, you know, let's conjecture an equilibrium exists of this kind. And then you work with the first order conditions to establish what is the equilibrium or what is the properties of this equilibrium, and then you continue doing that. Sometimes you also add, you know, some results at the end saying that this is indeed an equilibrium, but there is no, in many auction explications, the concavity of this problem is not really guaranteed. So like this first order approach giving you exactly the equilibrium characterization is not immediate most of the time. So this is called like first order approach. Yeah, and done in many auction papers. Anyway, all right. So let's do a simple application of this. So the first application of revenue equivalence principle is gonna be the all-pay auctions. So all-pay auctions, of course, like it is not as an auction format. It is not used in practice, but as you know, all-pay auctions are good description of some real-world phenomena such as R&D races, like contests, right? So everybody puts, effort to get, develop a drug that will cure some illness, and only the first company who does it will reap the benefits. Other ones don't get anything. Of course, in that environment, the revenue doesn't really make sense. But anyway, so let's do a simple application of all-pay auction. So all-pay auction rule is that the highest bidder wins, but everybody pays their own bid. So this is the definition of all-pay auction. So a very simple application of revenue equivalence theorem is that what is the equilibrium bid in an all-pay auction? This is like, let me write it, the all. Anyone? This might be interactive. Yes, just this one. It's just 0 to x, y, g, y, dy. Because basically, in an all-pay auction, you always pay your bid. And this has to be your interim expected payment. So this has to be your bid. So no matter what, whether you win, whether you lose, you always pay the same. And therefore, this has to be your bid. That's it. You solve for the all-pay auction. Another one is like interesting in a sense that like it is not used in practice, but just think about, we have at least 3 bidders. So now we don't have 2, but at least 3 bidders. And let's consider the case of third price auction. So the highest bidder is the winner, but the highest bidder pays the third highest bid. Not the second highest bid, but the third highest bid. This is interesting because, like, for instance, you can immediately conjecture, and it will be true, that in this equilibrium of this auction, everybody will be actually bidding higher than their values, right? Because in a second price auction, you bid your value. Now you only pay the third highest bid. So you will actually, in equilibrium, will bid higher than your value. So let's do this. So in a third price auction, M3X, this is like the interim expected payment in a third price auction by revenue equivalence principle should be equal to 0 to x, y, g, y, dy. The reason that I will quickly do this is it's like an interesting phenomena, and also like we will do some order statistics tricks. And thirdly, we will also argue something that we mentioned earlier, right? So we will find an equilibrium, but this equilibrium may not be always an equilibrium unless some conditions are satisfied. So in order to, so think about, I need to somehow understand the distribution of the third highest out of n random variables, right? So let's write this the following. So f, the small density of 2 out of n minus 1 of y, given that y1 is smaller than x. So I'm interested in, since I'm looking for a symmetric equilibrium, I am interested in the third highest, which means if I am the highest, the second highest of my opponents, right? So I am the highest, I am higher than the highest of my opponents, and I'm interested in the second highest among my opponents. Okay, so you can argue that this is equal to the following. So the first one, I'm going to, like, since this is a conditional density, I need to first divide this by the probability of this one, the condition being happening, which is f of x to the power n minus 1. Then I need to think about the density of it. And I can argue the following. I can argue that this is n minus 1 times fx minus fy times f1 of n minus 2y. Because basically so this is my value x, right? And I know that the highest among my opponents is smaller than here. And then I'm thinking of what is the probability that exactly second highest is here. Okay, exactly second highest is here. This means that the highest should be here. So the highest should be between X and Y. So capital X minus capital Fi is the probability that the highest will be in this region. And I can choose this highest in n minus 1 different ways because I have n minus 1 of these random variables. And then when that happens, this becomes the highest of n minus 2. Okay. So this is like a nice order statistics, trick that is used. And once you have that, then
Wait, so why don't you need to multiply n minus 2?
because what do you mean?
Because
N minus 1.
there are n minus 2 ways to choose the guy who is.
No, but I am saying that remember I'm relating the density, like that basically the density means the probability that the second highest out of n minus 1 is exactly at this value y. Okay, and then I'm saying that that event is equal to out of n minus 1, highest is in this interval, and I can choose that highest in n minus 1 different ways because I have n minus 1, opponents to choose from. But then when that happens, this is already representing the highest of 1, the highest of n minus 2. So I don't need to multiply this by n minus 2. But this is my best answer. I don't know if this satisfies you, but once I have that, then I'm going to write this one as m3x is equal to f of x to the power n minus 1 times expected value of beta 3, the equilibrium in a third price auction, y2, because I basically yn minus 1, 2, because the third highest is going to be the second highest among my opponents, given that y1 is smaller than x. And then I'm going to just have this as 0y, y, gy, dy. And since this holds for all x, 0 to x, I'm sorry, 0 to x. Since this holds for all x, then if I take the derivative of this also needs to hold for all x, right? So I take the derivative of both parts, and then on the left-hand side, I get x gx equal to the derivative of this thing, but basically, how do I get this? So I'm going to just so I'm going to have all these, so this one and this one will cancel out. And here I'm going to have integral 0 to x, beta of x, and the density, the whole thing, n minus 1 times the derivative of this one, which is the derivative of this with respect to x is just small fx. And then this one, f1 n minus 2 y dy. Okay. And then if I differentiate once more, then I get the following. So I will just leave the rest as a math exercise. So I will write the solution here. Beta triple x is equal to x plus f of x divided by n minus 2 times small fx. Okay. So this clearly shows that everybody will be bidding higher than their values, which is expected. But one thing that I wanted to tell you was that if you take the derivative of this with respect to x, under some conditions, this becomes increasing. So this becomes positive, but not always this is positive. So this would mean that for some f, actually this wouldn't result in positive. And that would mean that basically this is standard equilibrium because this is done, everything is done with the assumption that it is monotone. Okay. As an exercise, for instance, you can work on war of attrition. So war of attrition is another one that I'm not going to cover here. So war of attrition is an auction kind of format in which we have two bidders and highest bidder wins, but both bidders pay the smallest of the two bids. And this is we used in different contexts, but even in the evolutionary biology game theory context of two animals fighting with each other. And so they both put efforts to, to kill each other, and they both, have they both have this utility from doing that. But the one who is willing to stay more is winning, and therefore that's that kind of a game, war of attrition. You can use also Equino's principle to get an easier answer to find the equilibrium of war of attrition. Any questions? Yeah.
Are there any practical situation which is the third price auction is?
I know what actually. Practical situation is a PhD qualifier exam. All right, so let's continue with deviations from Equino's principle. And the first thing that we will talk about is going to be risk aversion. All right, so risk aversion, as you know, like so far we assume that when the bidders are calculating these wins and losses, right? They are just risk neutral, which means that they are multiplying the probability of something happening with the utility in that case. But in the real world, we know that many people are risk averse or risk seeking, most of the time risk averse, and actually in like many results in experimental auction actually shows that while participating in auctions, loss of risk aversion kind of behavior is observed. So it is important to understand. So for the risk aversion, I'm going to still have a symmetric model. So I'm going to still assume that there are n bidders. All of them are having independently distributed private values, and these are identically distributed, so it is symmetric. But the only thing that I will change is that rather than assuming that they will have a risk-neutral utility function, I'm going to assume that they are going to have a von Neumann utility function, which is strictly concave. So now, of course, this can be done in different ways, and the way that we will model, I really cannot argue that this is the most natural one. But think about the following. So, remember when with risk neutrality, we assume that in the case of winning, right? So my utility is X, my value, minus, for instance, think about first price auction, minus B times the probability of winning. Now let's not consider this X minus B or P, but U of X minus P, right? And U is not a linear function, or like it's not the identity function anymore. It's a concave, strictly concave function. So there is risk aversion. So whenever there is risk aversion, the decision makers prefers a certainty equivalent to a risky alternative, right?
Sorry, can I ask about the question about the third price?
So, yeah, of course.
Yeah, so in the bid function, so is that x plus f of x divided by
n minus 2 times.
So as the number of bidders goes up, does this mean that the bid goes down?
Yeah. This is another interesting phenomenon.
So what's the intuition?
The intuition, okay. Okay. So as the number of bidders go up, so basically like first of all, the expected revenue and everything will go up. So although the individual bids will go down, the expected selling price will go up. So it's going to be beneficial to the auctioneer. But I think this is the first time I'm thinking about it, but my thinking is something like when you have more and more bidders, you are getting closer to bidding your value, which is kind of like the natural thing to do, right? So like in a second price auction, you want to bid your value, and
and I guess another thing is that if you bid too high, and if there are many people, it becomes more likely that you have to pay more than the value.
Yeah. So there is like a negative utility. There is a negative utility. Ex post negative utility is possible here. Whereas like in a second price auction or a first price auction, it's not possible. Right? Yeah. So, but it's, I think I don't have a good answer to your question, but yeah, that's another interesting thing. But I don't know, like yeah. Okay, so everything clear with the model? So we are going to have, again, the same model. The only thing that we will change is that we will have a U of X minus P. All right. So when we consider second price auction for this case, this actually doesn't change anything again. So because my argument about the truthful bidding dominating the underbidding or overbidding did not have anything to do with the risk neutrality or risk aversion. Because for each possible case, no matter what the others would do, I was better off by truthful bidding, right? So the second price auction equilibrium doesn't change.
So just let me make sure. So
Yeah.
this is again, the function is U of X minus P.
Yes.
Where X is,
Yes, it's gonna be in next line. So now let's do the more interesting one, which is the first price auction. So in order to differentiate the bid function, bid risk aversion to the bid function with risk neutrality, now let's use this notion of gamma rather than theta. So this is like a equilibrium bid in a first price auction when the bidders are risk averse. All right. So again, we will use the same trick. We will consider a bidder whose value is X, but who is bidding as if his value is Z. All right. So the utility then is, again, with probability GZ, I'm going to win the auction, right? Because only when all the other bidders have values smaller than Z, I'm going to win the auction. But in that case, my utility is not X minus gamma Z anymore, but it's going to be U of X minus gamma Z, like basically U of XP, X minus P, the price that I will pay, which is my bid, all right? So if you differentiate this with respect to Z, then you get the derivative of the first part, which is small z, small gz, this times the second part itself, plus the derivative of the first function, which is capital GZ, times the derivative of the second function, which is U prime, I'm sorry, U prime X minus gamma D, times the derivative of inside, which is gamma prime Z. All right. And since there is a negative here, this becomes negative. So this has to be equal to 0 when Z is equal to X. So when you write X wherever you see Z here and rearrange, you get this. Gamma prime of X is equal to U X minus gamma X divided by U prime X minus gamma X times small g divided by capital G. All right. So, but as I also sanity check, actually, if you plug in U as a linear function, U as the identity function, then actually this becomes just like this whole thing becomes just X minus gamma X, right? Because like if U is like a linear function or an identity function, this just becomes you know, the function itself, which is X minus gamma X, and this just becomes 1. So for the risk neutrality case, in which we denoted by beta, we have this holds, beta prime is equal to this. For the risk aversion case, we have this holds. Now let us compare these two. Okay, so remember, like, I can also copy them here, but like keep this in mind. I want to just compare this and this. And what I will do is I'm going to argue that this is going to be greater than this. So basically, the risk averse utility function will have a higher slope. Basically, it's going to be steeper than the risk neutral bid function, because at the end of the day, our main result is going to be that with risk aversion in first price auction, the bids of like the equilibrium bids is going to be higher. Therefore, the risk averse bidders will have a higher expected payment, like expected selling price compared to second price auction. So I'm going to argue that this is going to be greater than this, and that's how I argue. So I'm comparing this, and this inequality follows from for any utility, for any function that is concave, U divided by U prime, U of Y divided by U prime of Y is greater than Y. Anybody knows why? You can do this in, I think, a few different ways, but I think you can do this by looking at, the one way I remember was if like U double prime is negative, which is this function being concave, then I want to argue that U is greater than y times u prime, and you can do this by, I think, when you, like, if you think about the derivative of this, like derivative of this one is u prime, and the derivative of this one is what? This one is u prime minus plus y times u double prime, right? The derivative of this one is u prime, the derivative of this one is u prime plus y double prime, like the second order derivative. So because it's a like product function, and you can see that this is obviously greater than this because this is negative. I'm sorry, this is u. I made a mistake. This is u prime. Also, this is y times, sorry, y times u double prime. And you can obviously see that this is greater than this because this is negative, right? Since the derivative is negative, when you take the integral, this also becomes, the left-hand side is also greater than right-hand side. So using this fact, what we can argue is that the for the same value, the gamma will be steeper than beta. And like we need to do a little bit more here, but I'm doing a little bit hand waving. So in order to complete that gamma will always be above beta, you need to say that whenever they intersect, gamma should be coming from below and beta should be coming from above, but this is not possible. So it will be actually like gamma will be always above beta, which would mean that when you compare risk-averse equilibrium and risk-neutral equilibrium in first price auctions, risk-averse equilibrium gamma is going to be higher. That means the expected selling price, expected revenue with risk aversion is going to be higher in first price auctions. But there was no difference between second price with risk neutrality and second price with risk aversion. This automatically then would mean that with risk aversion, first price auction generates a higher expected selling price. So this is summarized here. All right. So far, so good. Okay. So now let's look at a second deviation from. Right? Oh, okay. I need to go to this. Yeah. Go ahead.
So is it obvious that this form of the this functional form is right definition of the risk aversion?
No. So there are papers like there are some seminal work that actually consider this and kind of like use risk aversion for this specification, but no, there are some other papers that kind of question this and they say that basically this doesn't make sense because it's not like basically this value and the price is not even the same thing, right? So it's not, you know, your consumption value and the price is different. So like you could also have like another version is going to be like u prime of x, right? So like a u of x minus, for instance, price rather than u of x minus p. But like for this specification, we established this.
So does your result actually rely on the kind of specification of the utility function? Like
Yeah.
If you take some other different utility functions, you can potentially like it can be sort of like risk averse, then.
Yeah. So there are. Yeah. So I don't remember. I cannot off the top of my head. I cannot tell you when you consider like other specifications. So the specification that we consider is u of x minus p, right? And then we allow this u to be any concave function. You can do more if you assume, for instance, like this u is Cara or CRRA. You can get more results, and I think like we have some results on it. But if you consider some other value of concavity function, like for instance u of x then minus p, then you will get different results.
For the opposite thing happening, if it is in a case of risk loving case.
Risk seeking case, I'm sure the answer is no, but I cannot. You know, no. Yeah, I think the case of risk seeking, there is like in both theory and experimental and behavioral, there is like loss aversion is studied, risk aversion is studied, but risk seeking is somehow less studied. So, but I'm guessing like at least in this thing, you can work on your own and get some results maybe. But perhaps some papers already established it.
Is there any like the intuition behind like the result here? Like, the discover stage and actually it's more visibly.
Yeah, so the intuition is like, at least my intuition I can think about right now is something like, so when you like think about the trade-off between increasing your bit or decreasing your bit from some value like the equilibrium value, then the loss is if you increase your value, right? The loss is that whenever you win, you will have to pay this extra amount. Whereas your gain is you win with high probability.
Right.
So when you pass from risk neutrality to risk aversion, you are the increasing. I thought that I had an intuition, but right now my intuition tells me exactly the opposite.
Oh, I see.
So
Maybe you have any-
my intuition is associating this with Dutch auction. So in the Dutch auction, you at some point you raise your hand, and if you raise your hand, that's a sure outcome.
Yes.
But
Okay.
if you wait, that's a gamble, right? So you can get a high payoff, but there's some positive probability of not getting the item. So it's a sure outcome versus the gamble.
Yeah,
and
in this case, yeah. That
Yeah,
makes sense.
yeah,
Like,
I think that's a
discover
very, very good answer.
you are like
Thank you.
discover. That's right.
Okay. So now let's move on to a second deviation, which is so far we always assume that all the bidders are values are IID, independent and identically distributed. So we have a symmetric model, so we are focusing on symmetric equilibrium. But in the real world, also there are asymmetries between the bidders, right? So some we may still have independent and private values, but maybe some bidders are more likely to have higher values than others. And actually, this is going to be like how I will start my class on Friday when we are talking about asymmetric options with resale. And there are so many examples, right? So like some bidders may be more experienced, some bidders may have more, finances. So it is interesting to think about asymmetric options in which we have a number of bidders, but their value distributions are not necessarily identical. In order to start working on this, we can consider the simplest case of two bidders, one bidder weak, one bidder strong. Like, for instance, we can consider one bidder having a first order stochastically better values than the other bidder, right? So with symmetry, we have revenue equivalence and efficiency. And when we have these asymmetries, we are going to only consider two bidder case. And also our paper, BJ also has only considered two bidder case. We are thinking about how does this affect revenue and efficiency. I'm going to give you some results here, but the presentation Friday morning is going to give you more details and actually adding the resale part to it. Today I'm not going to talk about resale. So what's the model? The model is we have two risk neutral bidders. So we are back with risk neutrality. I don't want to change two things at the same time, right? So risk neutrality. But now the difference is that one bidder draws a value from F1, another bidder draws from F2. Okay, and we still have independence between them, so we don't like these two distributions are independent of each other. But we say that F1 is smaller than F2, which means like F1 of X is smaller than F2 of X for all X except for 0 and 1, which means that F1 first order stochastic dominates F2, which means like F1 is more likely to have a higher value than compared to F2. All right, so like in the many other applications, right? So let's consider first second price auctions. Does second price auction truthful equilibrium affected by this asymmetry? No. Still, in a second price auction, even with asymmetries, bidding the value will be a dominant strategy. So you will consider this equilibrium as the equilibrium, but we are interested in basically solving the first price auctions equilibrium with asymmetries, right? So now let's start with like the first, second price auctions. Okay. So since we have an asymmetric setup, we should actually like allow for, and it will turn out that way, asymmetric bit functions too. So rather than having only one beta, we are going to have now beta 1 and beta 2. And the inverse is denoted by phi 1 and phi 2. So beta 1 is equilibrium bit strategy of bidder 1, beta 2 is equilibrium bit strategy of bidder 2. Phi 1 is the inverse of beta 1, phi 2 is the inverse of beta 2. And you can actually, like if the values are distributed between 0 and omega 1 for bidder 1 and 0 and omega 2 for bidder 2, first of all, you can see that bidder with value 0 has to be 0. So this has to be holding for both bidders. And secondly, you can, maybe it's not that obvious, but not that difficult to see that the highest bids has to be the same too, right? Like, and I can prove this without using any, whiteboard, right? Because you have a question?
Yeah, so I kind of like can convince myself that indeed this is the case, but
Yeah.
does it depend on the case with two bidders? Because
Yes.
Maybe.
So two bidders. Like I think like once you have 3 or more bidders,
For the all-free auction version of it, I remember having a case in which support could be defined with three more bidders.
Yeah.
Yes.
yeah, all I'm thinking of is like 2 bidders. I'm not that sure about more bidders, but yeah. All right. So like, let's argue that the highest bid has to be the same, and like think about one bidder is bidder 1 or bidder 2's highest bid is some B prime, B upper bar. If the other bidder bids B upper bar plus epsilon, right, as the highest bid, anything higher, then if that bidder bids something smaller than this, but greater than this, the probability of winning doesn't change, but payment changes. Therefore, it is suboptimal. Therefore, the highest bid has to be the same as well. Now, let's do the equilibrium calculation. So now let me depict. So let's say that this is 0, this is omega 2, this is omega 1, and this is beta 2, and this is beta 1. And they both have the same highest bid. Now, let's consider one's expected payoff if he bids some B. If one bids this B, then the probability of winning is when bidder 2 has a value smaller than phi 2 of B, right? This is phi 2 of B. Because at phi 2 of B, beta 2 of phi 2 of B is going to be exactly B. So, and the probability that bidder 2 has a value smaller than phi 2 of B is F2 of phi 2 of B. And in that case, the utility is X minus B. So bidder 1 will try to maximize this. So now we will have another notion. So remember, phi was inverse of beta. Now let's call f of phi to be h. Okay. So I'm going to have this closed form as h2 of b times x minus b is the utility of bidder 1 who has a value of x and then who bids b. Okay. And in order for this to be an equilibrium, this needs to be maximized when b is equal to beta of x, or equivalently when x is equal to phi 1 of b, right? So let's differentiate this with respect to b. Then I get basically h of b. Actually, let me do it in the like a longer way. So by differentiation, I get. So the derivative of this one is F2 of phi 2b times phi 2 prime b. It's the derivative of the first part, right? Times the second part, which is x minus b, plus the first part, which is f capital F2 phi 2b, times the derivative of the second part, which is just minus 1, right? So this just becomes minus here and then equals to 0. And when you equate that, you get this expression. And you can rewrite this one as this one, okay? But this was done for bidder 1 by assuming bidder 2 is using equilibrium strategy. You can just change the indices and then you can say that a symmetric thing happened for bidder 2 as well. But the problem here is that, yes.
I lost, but what is the H function?
H function is F joint phi. So F of phi is H.
Okay, thank you.
But so actually, this is the first time that I'm not gonna able to tell you that there is a closed form expression for this. And the problem is the following. So when you are working with the inverse, like the working with bit functions or inverse bit functions are the same, right? You can just comfortably take the inverse of that. You get a differential equation, which is nice, but differential equation that involves bidder 2's bit function or the inverse bit function. And similarly, when you do the same for bidder 2's maximization, you get a differential equation, but it's not a separate differential equation. It involves bidder 2's function here. So this is called like a linked pair of differential equations. And in general, there is no, unfortunately, closed form solution to these problems. And even numerical solutions are difficult, right? So there is this paper by Marshall and Marx about like how to find numerical solutions to asymmetric curve price solutions. Because when you are doing when you do not have a solution to a differential equation, right? So you can always use numerical techniques. But in order for numerical techniques to work, you actually need to give an initial condition. But it turns out that for these asymmetric, if you give the obvious initial condition of like beta of 0 or phi of 0 is equal to 0, then there is this like 0 divided by 0 indeterminacy, right? So like because when you look at the differential equation here, this becomes 0 at b is equal to 0. So therefore, like it doesn't become tractable. So the solution that Marshall and Marx was able to do is like a shootout method. Basically, they kind of try different b upper bar levels, and they start the differential equation to start from there, go all the way down to 0. If it is like smaller than 0, then they increase the try, and so they do this numerical method. But there is no general solution. Okay. So, but we will have some partial results, and we will have I think I have time, so I'm going to also actually do an asymmetric uniform distribution solution with you, at least some part of it. Okay, so we will have. We want to understand basically, although we do not have a closed form solution to bidder asymmetric auctions, first price auctions. We may have some partial results. In order to get these partial results, we will assume something slightly more stronger than the regular first order stochastic dominance. So the regular first order stochastic dominance tells you that bidder 1's value distribution is below bidder 2's value distribution. So it is more likely that the bidder 1 will have a higher value. But there are different stochastic dominance notions, and dominance in terms of hazard rate, dominance in terms of reverse hazard rate, and a few others. The VJ's book has this nice appendix in its talk. But let's say that we consider a reverse hazard rate dominance. So we assume that not only F1 stochastic dominates F2, but its stochastic dominates in this fashion. And this is not a very strong assumption. I think, for instance, this is satisfied when like F is, some F1 is F2 to the power some alpha, for instance. This will be satisfied for alpha greater than 1. And this is like an assumption also used in other like mechanisms and other literatures too. So the reverse hazard rate stochastic dominance. So we assume this, and then we can get the following two results. The first one is that I'm sorry. The first one is that the weakness lead to aggression in the sense that weak bidder, if I consider the weak bidder and strong bidder, bidder 2 and bidder 1, for the same value, bidder 2 will be bidding more than bidder 1. So bidder 1, like basically bidder 2 will be more aggressive. But to counterbalance that, if I look at not the equilibrium bids, but the bid distribution of bidder 2, bid distribution of bidder 2 will be stochastic dominated by bid distribution of bidder 1. So like how can this be? Because like although bidder 2 for the same value is bidding more than bidder 1, bidder 2 is less likely to get higher values, right? So if you look at the bid distribution for bidder 1 will be higher. So let's prove this. So there is no proof here, and so like this is one example, for instance, when the values are between 4/5 and 4/3. This is like bidder 1's equilibrium bid. This is bidder 2's equilibrium bid. And as you can see, for instance, here, this allocation is inefficient, right? Because like let's say that if the value is 4.5 for bidder 2, and like slightly like here, so this is 1 for bidder 1. Bidder 1 has a high value, but bidder 2 wins the item. So that's why like we will consider asymmetric auctions with resale on Friday, but not today. So let me give you the proof. Now it's not that difficult, but okay. So I'm going to, for the proof, basically what I will do is then we will do mechanisms. I'm going to just use these two first order conditions, okay? So proof of this proposition. So I want to say that when these two, okay, so let me first draw a picture here. I want to say that when I consider like this is beta 1 and this is beta 2 potentially, when they intersect, because of this formulation, okay. So like let's say that phi 1 of C is equal to phi 2 of C, which is equal to Z for some C in the 0 to B upper bar. Then phi 2 prime of C from the first order condition in the previous page, it's going to be F2 of Z divided by small f2 of C, because like remember this was F2 of phi 2 of C, which is Z, times 1 minus Z minus C. And phi 1 prime of C is similarly F1 of Z divided by small f1 of C times 1 minus C minus C. Okay. And when you consider this inequality, you can see that this is correct. So basically, for whenever they have the same value, phi 2 will have a higher derivative than phi 1. So this means that whenever they intersect, beta 1 should be steeper than beta 2. But if that's the case, like remember beta 1, like if that's the case, like let's say that they intersect at some point, okay? And beta 1 is going this way and beta 2 is going this way. Can they ever intersect again? No, because for them to intersect again, right, beta 1 should be less steep than beta 2. This never happens. This means that except for 0, they never intersect, and beta 1 will be always higher than beta 2. This means that for the same value, strong bidder will be bidding higher than bidder 2, weak bidder. Okay, this is the first part. And similarly, I'm not going to take now too much time. Similarly, due to the exact reason, you can show that the reverse holds when you consider bid distributions, right? So this is about the bids. For the bid distributions, the reverse holds. And this needs to be the case, right? But because it makes sense. So the reason that the bidder 2, who is the weak bidder, is more aggressive than bidder 1 in the sense of bidding higher is because bidder 2 is facing a more aggressive bid distribution than bidder 1, right? That's why bidder 1's bid distribution should be dominating bidder 2's bid distribution, whereas bidder 2's function should be above bidder 1's bid function. Is this clear? All right. So how much time? Oh, no, I have only 30 minutes left. So I was hoping to give you an example of asymmetric uniform value distributions in which actually a closed form expression is available. And actually Plum has generalized this to asymmetric power distributions. And some interesting things can be said. But let me just summarize because we have only 30 minutes and I want to also tell you like the mechanisms and the optimal mechanisms in general too. So the BG's book has this discussions. So basically, for the asymmetric uniform distributions, you can show that first price auction generates a higher utility than second price auction. This was generalized by Maskin and Riley's asymmetric auctions paper. So Maskin, since there is no real easy closed form expression for the equilibrium in first price auctions, it is difficult to rank the first price and second price auctions in the presence of asymmetries. There are some sufficient conditions that are given, and unfortunately, the best of them still was a long time ago, so not many people has worked on it. Maskin and Riley showed that under two sufficient conditions, asymmetric, the first price auction generates a higher revenue than second price auction, and there is another one in which second price auction generates a higher revenue than first price auction. So the thing that I'm skipping is giving you more explicit details about it, right? So, but I think thing to understand from here is that with asymmetries, there is no general revenue ranking between first price and second price auctions. Under some conditions, first price auction generates a higher revenue. Under some other conditions, second price auction generates a higher revenue. Okay. I will skip some parts.
Is
Now,
there any understanding or perception which of the assumptions are more likely to be?
I would say at least Maskin and Riley's three conditions are not less reasonable for the one that makes second price auction better, right? So maybe I can tell you a little bit more on Friday because I'm going to also talk to you about asymmetric auctions. But basically, it is when Maskin and Riley's result is that when F1 is obtained by a stretch from F2, or in this way or that way, first price auction is better. But when you have some kind of some probability mass going to the lower values for F, the strong distribution F1, then second price auction is better. I would say the one that is used for first price auction revenue superiority is slightly more natural. Okay, so let's go over to okay. Mechanisms. So we are going to do basically yet another version of the revenue equivalence theorem, and then very quickly tell you the main result for the Meyerson's optimal auction. Okay, so when we say auctions, right, it looks like a specific kind of a game, right? So we have bids, we have some kind of anonymity, we have, but we can also think about many other kinds of mechanisms, right? So negotiation is one mechanism, right? Our posted prices is another mechanism. So we can have a more general setup in which again we will have incomplete information, private information. So we will have a number of risk neutral buyers. They will all have some values. So it's going to be also private value setup from, let's say, the 0 to WI. So we allow for them being different. So now we don't assume symmetry. We assume these value distributions are agent specific. And let's say that seller's value is 0. Then we can consider a selling mechanism in which there will be some messages or strategies or bits that are used. And there is going to be some probability of winning, and there is going to be some expected payment. And we are considering an equilibrium strategy denoted by beta I for player I. Okay. So some of you are very familiar with this. Some of you maybe not that much, but now we are going to introduce a very important concept in mechanism design called the revelation principle that allows the indirect mechanisms to be converted to direct mechanisms, because working with direct mechanisms is much easier than we can get like optimal mechanism kind of results once we constrain ourselves for these kind of like a specific structure. So what is a direct mechanism? In the direct mechanism, we require the message space to be equal to the value space. So rather than allowing different kind of messages to be used, we are going to only consider a revelation of their values, right? So here, Q and M again is similar to earlier page, like they are representing the probability of winning and the expected payment. But now we will not consider arbitrary message space. We will only consider the message space equal to the different values, all right? So we say that a direct mechanism is incentive compatible if truth telling is an equilibrium, all right? And the payoff is given by this. So like if I have, if the rest of the agents are announcing their types truthfully, X minus I, so I'm taking an expectation over this. This is the probability that I win if I announce Xi, and this is the payment that I will make if I announce Xi. So basically it's very similar. So the probability of winning will be only a function of my announced type. Okay. Okay, so I don't even differentiate here. So this is the equilibrium payoff, right? So this is in the equilibrium, this is the probability of winning times my value, and this is the interim. Basically, it's the payment, it's the ex post payment, and I average this out for all possible value distribution of my opponents. All right. So let's talk about the revelation principle. The revelation principle tells me that if I consider any kind of mechanism, it doesn't have to be a direct mechanism. It can be any mechanism in which the different messages can be used. Once I fix an equilibrium notion and an equilibrium result of an indirect mechanism, I can create a direct version of this mechanism in which outcome will be the same. So therefore, it's going to be without loss of generality, just to focus on direct mechanisms, because whatever I can do, whatever equilibrium I can achieve with indirect mechanisms, I can also achieve with direct mechanisms. Okay, and the idea is very simple. The idea is that, okay, so they have values, and in the indirect game, they can tell me what the bids are, but then these bids will result in some outcomes, right? And they will do some equilibrium calculations, right? They are going to, correctly in a Bayesian-Nash equilibrium, for instance, I need to fix the equilibrium, right? So let's say that I'm fixing a particular Bayesian-Nash equilibrium of this game, right? So in this equilibrium calculation, they are correctly guessing each other's strategies, and then they are giving a best response. So rather than them knowing their values and doing the equilibrium calculations, I do the equilibrium calculations for them. I just ask them what value you will have. Okay, and like think about this as like the first price auction, right? So in two-bidder first price auction, we already established that bidding half of your value is the equilibrium. So rather than they playing a first price auction, I tell them, okay, so the first price auction game is being played here. Tell me your value, and I will input half of your value in the first price auction, something like that. So this is going to be like a direct representation of first price auction. Okay, now since we have revelation principle, then we can use this revelation principle to get something like more stronger version of revenue equivalence principle. So, and then we will also get to the optimal mechanism to selling an item, and that where we will end our lecture.
Yeah,
All right.
can I ask just one
Yeah.
question about that direct mechanism?
Yeah.
I know, I can say that one of the examples for direct mechanism is just a standard auction, But what could be the examples of indirect mechanism in the real world or practically?
No, like first price auction is an indirect mechanism. Even second price auction is an indirect mechanism.
Why would that so? You just report your value.
No, in a first price auction or a second price auction, I don't ask you to report your value. I ask you how much would you bid. Yeah, so like in second price auction is a little bit confusing in that sense, because like truthful bidding becomes an equilibrium, but still second price auction is not a direct mechanism, right? Because literally when I ask you to participate in the game, I'm not telling you, tell me your value. I'm telling you, well, how much would you bid in this game? So the bid space is not necessarily equal to the value space. Okay, so let's do this. I'm going to like this in. Now we are focusing on direct mechanisms, and remember we had this capital Q, right? The capital Q in the previous pages were representing the ex ante payments, ex ante probabilities of winning. I'm sorry, ex post probabilities of winning and ex post payments. But once we are considering a Bayesian-Nash equilibrium, I care about interim ones. Okay, so let me write this here. So I'm going to now write the interim one as Qi of Zi. So if I have bidder I who behaves as if, like, who basically announces her type as Zi is equal to integral capital X minus I for different value realizations of the rest of the players, capital Qi, Zi, comma, X minus I, small x minus I, F minus I, X minus I, dx minus I. So this is like basically an n minus 1 integral. So like x minus I means that there are n minus 1 possible values of my opponents, right? So like this is a compact way of writing. I'm just taking an expectation over the type space of all of my opponents. And similarly, so this is the interim probability of winning. And the interim payment mi zi similarly integral capital X minus I, capital Mi Zi X minus I, F minus I, X minus I, dx minus I. So once I have these interim probabilities of winning and interim payments, then I can write this one as my utility when the equilibrium utility, I'm first writing the equilibrium utility of having a value of xi is nothing but the interim probability of winning Qi xi minus mi xi, right? So this is the interim probability of winning. This is my value, and this is my interim payment. All right. So, and for this to be incentive compatible, for truthful revelation be better than any other revelation, this function here should be equivalent to this function. What is this function? This function is I am considering not necessarily truthfully revealing my type, but I'm considering possibly revealing any other type, Z, and the maximum of this among all those, okay, in equilibrium has to be, of course, equal to Z equal to Xi, right? So now, if I consider basically my equilibrium utility to be this function, since this function is a maximum of affine, or a fancy way of saying linear functions, whenever you are considering maximum of affine functions, that function is necessarily convex, and also it's called absolutely continuous. So you can use some methods. Right? Envelope theorem applies, and then when you are taking the derivative of this with respect to basically x, you can just like treat these as constant due to envelope theorem, okay? And then you get this result. So this tells you that the shape of the equilibrium utility function is only determined by the interim allocation probabilities. Okay? So when you take the integral of both parts, then you get ui of xi is equal to ui of 0 plus 0 to xi qi t dt. Okay? So this also necessarily means that the allocation function, like the probability of allocation, has to be a weakly increasing function, and this is called like the payoff equivalence. So this means that, again, like this, I earlier told you that in all standard auctions we have revenue equivalence and interim expected payment equivalence or payoff equivalence. Now we just generalize this, right? Because in those cases, the allocations were always efficient. So the interim probabilities were fixed to be 1. Now, this is saying that the allocation function actually perfectly determines the utility function, the payoff function of the bidders. Okay. So therefore, for instance, I think I mentioned this last time, but let's say that we have 2 mechanisms. They are not efficient, but they are generating the same outcome in terms of allocation probabilities. Then they necessarily will give the same payoff up to this constant. Okay, let's say that like this is 0, for instance, everybody whose value is 0 is getting 0. And therefore the same expected, for instance, revenue. So the revenue equivalence theorem is the new version of revenue equivalence theorem is this one.
I see. So is
Yeah.
the previous one that you showed this morning?
Yeah.
Basically, the special case of
Yes.
both in terms of the conclusion, but also the derivation. Actually, I already
Yes,
forgot that.
this derivation is easier, right? So like the results were less general and a little bit more difficult to show. Like when the results get more and more general, you just like use a few things. You say that this is like a convex function, so the first order condition is enough, and then you can take the derivative. You can take the integral because these are absolutely continuous, and the envelope theorem applies. So everything is like much simpler. There we did a little bit more work.
Then the first I forgot how you did it in the morning.
Good one. Yeah, there we were more into the details. But basically, like this is saying that when you have that was the second whiteboard here. So basically, like the functions they will have the same shape. The only difference that they can have if they have the same Q is due to this first term, ui of 0. And this you can see, right? So like I had to have this caveat, right? So I cannot say that all standard auctions will have the same revenue. Why? Because what if I say that I'm going to give everyone $1 and then run a first price auction? Is this a mechanism? Is this an auction? Yes, it is, but my utility is then minus n, less than my So this constant integration here, the first part is important, but up to that part, the shape is perfectly determined by the allocation function. This is, and the revenue equivalence is that basically from the utility function, you can get to the interim expected payments. And interim expected payment is given by this formula. Okay. So that's it. So with this interim expected payment, I am now going to give you the last couple, basically the optimal mechanism, and I will end there. Okay, so this is the payoff equivalence, and instance compatibility is there. Instance compatibility means that the function shape, U function shape, is perfectly determined by as the derivative by the interim allocation probabilities. Okay, now, so now let's in the last like 10-15 minutes, let's solve for the optimal way of selling one item. Okay, the Myers's optimal auction very quickly. Okay, so something that we did not consider that seriously was a second condition called IR, right? Individual rationality. So when we have a direct mechanism, we require them to be truthful, so the incentive compatibility condition should hold. The truthful revelation of the value should be better than some other like lines doing something else. But also another condition is that nobody should be nobody should be worse off by participating in this mechanism, right? So of course this can be done in different ways. This can be like ex post or interim or ex ante IR. But now let's consider this to be interim, okay, here. Like if I also have gamma x minus I here, that would have been ex post. If I do not have x here, then that would have been ex ante, right? So since incentive compatibility already gave us the Q function should be increasing, and that already gave us the U function should be increasing, this would IR would be could only bind for the lowest valued bidder, right? So the only thing that we care about is that, like for the zero value person, you will not be able to charge him a positive payment, right? Because this zero value person, even if I give this person the object, he will not get any benefit. So if I charge him a positive amount, his utility will be negative, and that will not be individual rational. So the payment to the zero type should not be positive, and this is enough to get IR for the rest of the players, because I know that the equilibrium payoffs will be will be increasing. All right. So now this one. Okay, so this is like how I don't want to say it. Like this is how Myerson got Nobel Prize. Of course not. All right, so but this is fun, and I don't think you will even need 30 minutes. So at the end, I will have some time if you have any questions. So I want to maximize the sum of interim expected payments of all the players, right? So I'm going to sum over for all I the expectation of the interim expected payment, which will give me ex-ante expected payment for a bidder. And when I sum this over for all I, that I'm going to get my expected selling price, right? So the expected revenue. So subject to IS, IC, and IR. So IC will be like, we are going to basically like just use the the payoff equivalence result, and then assume that IC will hold. And the only thing that will be required for the IR to hold will be this one, and it will be obvious that this is not going to be a weak inequality. This has to be equal to 0 for the optimal option, right? So this is going to be, but the thing that is like nice here is this changing the order of integration and combining it together. Okay, so let's do that. From the payoff equivalence result, so I'm going to let me just do this only for one agent, okay? Just for agent I, okay? E of MI, capital XI, is equal to integral from 0 to WI. So I'm varying the values of agent I, and inside is basically what was written in the previous slides, which is the payoff equivalence result. MI of 0 plus QI XI times XI minus 0 to XI QIT dt. And this multiplied by FI XI dXi. Okay, so I'm varying values of XI. All right. So from here, this can immediately go out because this has no XI in it. Right. And now I'm going to divide the rest of them into two. One of them will have only one integral, other one will have double integral. Okay, so MI of 0 plus 0 to WI, the first part, XI, QI of XI, FI, XI, DXI, and minus. Now I have this double integral, right? So 0 to W and 0 to X. Let's again do changing order of integration here once more. So this morning we did it, now let's do it again. So here, the t varies from, right? So this is like x varies from, so this is x-axis and this is t-axis. X varies from 0 to w, right? And t varies from 0 to xi. Right? So we are going to consider all the possibilities here. Now, if I change the order of integration, then I can rewrite this one as 0 to wi. Now, like t will be outside, x will be inside, right? Now it's gonna be, since t has to be smaller than, I'm sorry, this is t, this is xi. T has to be smaller than xi. Now I'm going to have xi here and w here. Then fi xi, dxi, and the rest, like qit here. Okay. Now this just becomes, this part just becomes 1 minus f of xi. So this is how I get it. And just basically, I then change everything to this xi's to t to make it like look nicer. Okay. So second part becomes this. And now all I do is I combine these two now, and our nice virtual valuation appears. Okay, so the first, like this qi xi, fi xi is common for both terms. And in the first term, I have xi. In the second term, I have 1 minus fi, but there is this extra term of fi. So I divide this, I subtract, rather than just like not having this here and multiplying this by fi, I still keep this here and I have this expression. And this expression is the virtual valuation. And the nice thing is that basically, if I do this way, then this qi, fi, xi just then becomes, so remember, like this q already had an integral of all bidders except I, right? All bidders except I. With the additional integral here for I, this becomes the integral of all bidders including I. So now I can take this back to our ex post allocation, and make this overall values for all the agents. Now this becomes like a very magical, very easy, because like I was trying to solve a problem in which like I'm trying to decide, you know, even in a probabilistic sense, which one should I allocate? But all of a sudden, this just became, you know, a question in which like for instance, if you try to allocate weights, like if you try to allocate weights to multiple options, right? To maximize a weighted average maximized, then the solution is easy. Give all the weight to the maximum. That's it, right? So it just becomes that kind of a problem. So from here, all it turns out is that in the Meyerson's optimal auction, what we are going to do is I'm going to look at not the values, but the virtual values for all the players. And just I'm going to allocate to the bidder with the highest virtual value, so long as this virtual value is negative, is not negative, right? Because if it is negative, then you know I can also say that I want to keep the object, right? Because this is actually making me a loss. It's not really making me a loss because there is this additional part, but that it doesn't make sense to allocate when you know, to a bidder with negative virtual valuation, because it's gonna give you like a negative part. So the solution from all this, like with this, just by doing changing the order of integration, just this function just magically appears, and then we just say that the solution to like selling the optimal mechanism for among all possible mechanisms that we can think about, the best way you can get, you know, is to just look at their virtual value and give to the bidder with the highest virtual value, so long as this virtual value is non-negative. That's it. That's the solution of Meyerson. So basically, the solution is Qi of X is equal to basically, I can also ignore the ties, right? So let's say that we have two or more bidders, they have exactly the same virtual value and they are the maximal among all the ones, that any kind of distribution among them is going to give me the same thing, right? So I'm going to ignore that. So it's going to be 1 if virtual value psi. How do I let me call this psi of x. Psi I of xi is greater than or equal to, strictly greater than the maximum of psi j of xj for all j not equal to I. So if I have the highest virtual value, I'm going to get the object. If I if maximum of this and 0. So if I do not have a positive, then I will not get allocated. So that's it. That's like the Myerson's optimal allocation, and the virtual valuation is there. So like for the general case, right? So since I allow the bidders to be asymmetric, bidder 1 and bidder 2 may have different value distributions and therefore may have different virtual value functions, and therefore sometimes bidder 1 will have a higher value, okay, but will have a lower virtual value. Therefore, bidder 2 will be allocated the item. And actually, it turns out that we have a similar result, like so similar to the asymmetric auction, like the weakness lead to aggression kind of result. Weak bidders in Myerson's optimal auction will be favored. So weak bidder for the same value is going, or slightly less value will get the item in the optimal auction because of the value.
Asymmetric case.
This is the asymmetric case. This is the asymmetric case. So there is inefficiency, sometimes misallocation, sometimes no allocation. And for the optimal mechanism is this is actually showing that for different value distributions, you will have different phi, and then that will give you inefficiencies or misallocations. But if you go back to our the initial analysis of symmetric case, then since all the value distributions are the same, then all the virtual valuations are the same, and therefore there will not be any misallocation. Okay, but there will be inefficiencies due to the case that the auctioneer is keeping the object to himself. So it turns out, and of course this also depends on the assumption, like the mild assumption that the virtual value function is increasing, right? So virtual value function, when virtual value function is not increasing, then we cannot immediately apply this. Myerson has this like ironing technique, right? So you have this like if the virtual value function has this kind of a shape. So, and it's actually like not for all value distributions the virtual value function is increasing, but for most value distributions, like many of them practice to use or low concave functions or other many like a wide variety of distributions, virtual values are increasing, but sometimes they are not increasing. If they are not increasing, you do this like ironing, which is like you consider a transformation of it, which becomes weakly increasing and will satisfy some properties. That's a detail that but let's ignore that and let's consider the case in which the value distributions are such that the virtual value is also increasing. Then the optimal auction, when we have symmetric bidders, is very simple. Any standard auction in which the reserve price is set to the reserve price is chosen to make the virtual value is exactly equal to 0. So for instance, for uniform distributions, this is 0.5. Okay, so that's exactly 3 p.m. So let me end it here, saying that the standard auctions that we talked about earlier are in the symmetric setup that we considered will be efficient and they will all generate the same revenue, but they are suboptimal for maximizing the revenue. And to maximize the revenue is simple for the symmetric case. This is just again use any symmetric mechanism, any standard mechanism, where the virtual value equal to 0, like the pi inverse of 0, is the optimal reserve price. And for uniform distributions, it is half of the value distribution. Okay.
Any questions or comments? I guess if you have a long question, you can always ask.
Yeah.
Okay, so I have some questions that I will ask.
Okay, sure.
Okay, so on the note, let's thank the speaker. Thank you very much.
Sorry, I had to. Okay, yeah, I'll see you later.